Hello everyone and welcome to my YouTube channel, The Physicist. So in this video we are going to discuss the longitudinal waves, traveling waves or the progressive waves. We'll discuss about wave fronts and the ray, and we will see about the examples of waves and also some types of waves. Okay, in the previous video we have discussed in general what waves are, and we have also discussed about oscillations and the transverse type of a wave. Okay, and in the transverse wave we saw that the oscillations of the medium are perpendicular to the direction of propagation of the transverse wave. Okay, that's why they are called transverse waves. So now we will discuss longitudinal waves. Okay, so first let me draw a figure. So consider a pipe, a very long pipe filled with air. Okay, so we have a piston here, and this piston, okay, so in here there is air in this pipe. Okay, so we can set up a sound wave in here. Okay, we can set up a sound wave. Okay, in this air filled pipe, just by moving this piston. Okay, this is a piston. We can move it back and forth. Okay, back and forth, and we can generate a sound wave. We can set up a sound wave in this air filled pipe. Okay, because now if we consider this air molecule or air element, then it will follow the oscillations of the piston. Okay, so the oscillation will be in this direction. Okay, this is it will first go like this, and then it will come back to the mean position, then it will go this side. So the air molecules in the pipe also will oscillate back and forth with the piston. Okay, so because the oscillation of these elements of the air, okay, are parallel to the direction in which wave travels, we see that the wave travels in this direction. Okay, the waves travels in this direction with some velocity v. Okay, and the air element is oscillating parallel to the direction in which the wave travels. Okay, so this type of wave is called longitudinal wave. Okay, so we can draw a wave in it. Okay, so let us draw a wave in it. So like this. Okay, it will consist of some rare portions and some of the dense portions where air molecules are very close to each other. In the rare portions, the air molecules will be far away from each other as compared to the this dense portion. Okay, so the wave will look like this. Okay, so there will be alternatively some dense portions of the air and some rare portions of the air. Okay, and this disturbance will travel with velocity v in this direction. Okay, so this type of wave is called a longitudinal wave. Okay, So this figure shows how a sound wave can be produced by a piston in a long air filled pipe. Okay, if you suddenly move the piston rightward and then leftward, okay, if you suddenly move the piston rightward and then suddenly uh, leftward, okay, then you can send a pulse of sound wave. Okay, so you can uh, send a pulse of sound, okay, by just moving it once rightward and then leftward. Okay, so what will happen in doing so? The rightward motion of the piston uh, moves the elements of the air that are next to it rightward. Okay, so changing the air pressure there, and the increased air pressure then pushes rightward on the elements of the air somewhat farther along the pipe. Okay, so these air molecule will push on these air molecule due to the air pressure. Okay, so moving the piston then leftward reduces the air pressure next to it, and then farther elements move leftward. Okay, so they will move leftward. Thus the motion of the air and the change in air pressure travel rightward along the pipe as a pulse. And if you push and pull on the piston in simple harmonic motion as being done before, a sinusoidal wave travels along the pipe. Okay, so this wave will be, if this is the harmonic motion, if this is simple harmonic motion, then the wave will be a sinusoidal wave. Okay, SHM oscillations will lead to sinusoidal wave. Okay, so we'll get a sinusoidal wave. Okay, because the motion of the element in the air is parallel to the direction of the wave's travel, the motion is said to be longitudinal and the wave is said to be longitudinal wave. Okay, example is sound wave. Okay, example is sound wave, and it is the example of 3D wave, three-dimensional wave. Okay, and we are also familiar with the waves on the water surface. Okay, if we throw a pebble in the still pond, okay, for example this is the still pond, and if we throw a pebble into it, so there will be the water surface will be disturbed, and there will be some circles that are going outward. Okay, these circles are going outward from the point where we throw the pebble. Okay, so when this pebble is thrown into the still water of the pond, ripples are produced, okay, which spread out slowly outward in ever widening circles. So these circles are ever widening. This means the width of the circles is increasing time to time. Okay, so but see, the water particles of the medium, they do not travel along with the wave, but they only vibrate up and down. If the particle is here in the pond, then it will vibrate up and down like this. Okay, about its equilibrium position. So what is the equilibrium position? Equilibrium position was this position, which is represented by this line. Okay, so we identify the wave motion with the help of crest and troughs. So there are some crest is this peak, and the valley is called trough. So this is crest and this is called trough. Okay, so we identify the wave motion with the help of these crest and troughs. Okay, so as they traveling away from the center of the disturbance, this was the so here was the center of the disturbance, and these crest and troughs travel away from it. Okay, so these waves are two-dimensional waves. So these waves, that is water waves, these are two-dimensional waves. Okay, and as an example of three-dimensional wave, we can consider a point source. Okay, a point source of light, for example a bulb, if you are very far away it will look like a point. Okay, a point source of light emits light wave in all directions. So this point source will emit light waves in all direction in its surroundings. Okay, in this paper or in this plane, it is looks like that it will radiate into a circle, but the actual radiation is going in all direction into a spherical way. Okay, so these waves spread out uniformly in the ever increasing concentric spheres. Okay, so this is the, for example, if this is the light source, then the light wave will go in ever increasing spheres. Okay, this is a sphere, for example. Okay, so this is a sphere. Okay, and the light waves travels with the velocity 3 into 10 raised to power 8 meters per second. Okay, and this is the example of three-dimensional wave. Okay, so now let us discuss traveling waves. Traveling waves. Okay, so both the transverse waves and the transverse waves and the longitudinal waves, they both are called traveling waves. Okay, they both are called traveling waves, or also called progressive waves, because they both travel from one point to another point. For example, in there the wave travel from, for example, from this point to the corresponding different forward points. Okay, so wave travels from one point to another point, so that's why it is called a traveling wave or a progressive wave. Okay, so this is longitudinal traveling wave, and before we discussed a wave on a string, and this was a transverse traveling wave. Okay, and also note that it is just the wave that moves from end to end, not the material. For example, string in this case and air in this case. Okay, so a progressive wave, that is a traveling wave, consists of a sequence of waveforms. So this is a first waveform, then another waveform. So it consists of a sequence of waveforms. Okay, and what does these waveforms do? They transfer energy outward from the source. Okay, so the energy is carried out by the waves. So this source is emitting its energy in these waves. Okay, so these waveforms transfer the energy outward from the source. Okay, for example, that pebble you throw in the water pond, okay, so its energy is transferred to the different regions of the water by these waves. Okay, so for example, if this is a wave, okay, if this is a wave, then of course in between this is called the equilibrium position. This will be the equilibrium position, and this will be the called the amplitude of wave. Amplitude of wave. Okay, this amplitude of the wave can be represented by A. Okay, so the amplitude of a traveling wave that is produced by a point source gradually decreases in moving away from the source. Okay, we see that the pebble, where we throw the pebble, the waves are higher, then the amplitude becomes, okay, so amplitude decreases as the wave move outward. Okay, so we see that these type of waves, the amplitude is inversely proportional to the r, where r is the distance of the point of observation. For example, if this is, there we are observing the amplitude of the wave, so r is the distance of the point of observation from the position of the point source. So this is the distance r. Okay, so we can say also intensity. Okay, if we want to calculate the intensity of a wave, okay, we know that it is proportional to the amplitude square. So since amplitude is inversely proportional to r, so we see that intensity is inversely proportional to r square. That is, we can say that intensity of a square wave falls off as 1 over r square. Okay, so now let us discuss the wavefront and the ray. So as we have seen that wave starts from a source. Okay, waves starts from a source and then spread out into new and new regions of space. Okay, for example, ripples on the water surface start from the point of disturbance and expand in the form of circles. Okay, and these circles are in fact the crest of the waves. Okay, what we see as a circle on the surface of water, these are actually the crest of the waves. They are they are above the mean position. Okay, that's why they are called crest of the waves. Okay, and all the particles located at the crest, okay, like if this is the circle, if we are considering this circular wave, then this, if this is the crest, then on all the particles that are located on this crest will be in the same state of oscillation. For example, if, because they are in on a crest, so they will all will be after the crest they will start following this path, or they will be start coming down. If we see the this surface particle on the surface of water, so when it is at crest, it means that this particle is at maximum displacement from its equilibrium position, so it will be ready to go down from this position. Okay, so all the particles that are on the crest will be in same oscillation state, which is on the crest is having their maximum amplitude. Okay, or we also call they are in same phase. same phase. So all the particles that are on this circular crest, they will be in same phase, okay, also called the same oscillation state. Okay, so the continuous locus of all the particles, so all that particles, okay, and their continuous locus. A locus means a path. Okay, so if we connect all these particles, a circle will be formed. Okay, so the continuous locus of all these particles which are in same phase is called a wavefront. So because on a crest all the particles are in the same phase, so the locus of these particles will be called the wavefront. Okay, so this is representing a wavefront. Okay, but the particles which are next to, for example, this particle, okay, so next to this particle they will be like a somewhat below than this particle. Okay, so and coming upward, so they will also make a circle which is a little bit inward the crest circle. Okay, so this is a different waveform or different wavefront. Okay, so these all the particles on this circle will all be in same phase, and this will also consist of a different wavefront. Okay, and also particle next to it will be a different wavefront, and similarly all these particles will have a different, will be on different wavefront. Okay, so when we make a surface, okay, which passes through these points and completely surround the source, this is called the wave surface. Okay, for example, if we consider a 3D example of wave, for example a point source, okay, if this is a point source of light, okay, point source of light, then it will emit spherical waves. Okay, all the points on these spheres will be in the, okay, so all the points on the sphere which is concentric, which has the center as the source, okay, they will all particles will be in same phase. Okay, so this is called wave surface. So this will be the wave surface. So the question arises, what is the difference between wave surface and wavefront? Okay, what is the difference? See, the wavefront can be represented like this. Okay, we can take a portion of this surface and we can call this as a wavefront. Okay, but the wave surface is the whole surface. Okay, okay, so okay, so in case of water ripples, the wavefronts are circles, whereas in the case of point light source they are sphere. Okay, so in diagrams the wavefronts are often shown connecting crests or troughs. Okay, so the wavefronts are shown in by connecting the crest or troughs, but in fact any surface connecting points of equal phase is a wavefront. The propagation of wave is visualized by advancing wavefronts. So these wavefronts are advancing Advancing means they are moving forward. Okay, so the stationary wave surface is remains behind. So this is also the difference between a wave surface and a wave front. So the surface that leaves behind is called a wave surface. Okay, previously it was a wave front. Okay, but the wave front moves forward. Okay, the wave surfaces are separated by one wavelength. Okay, so if this is a point source, as an example of water waves, this is our first circular wave, this is second circular or second crest, we can say. This is first crest, then this is second crest, then this is third crest. They are separated by one wavelength. These are the wave surfaces. Okay, these are the wave surfaces. If you don't know what a wavelength is, okay, so don't worry, we will discuss what a wavelength is. Okay, so these circular waves or the spherical waves at a considerable distances from a source, they will become very large. Okay, if we go to a large distance, the wavefront will become very large. Okay, and small portion of it can be considered as nearly planar. So this is a nearly planar. Okay, so in that case, this is called planar wavefront. This is called planar wavefront. Okay, so if the point source of light is placed at primary focus of a convex lens, okay, if this is a convex lens and if this is the focus and we put a point source, okay, point source there, so this the point source will emit the spherical wavefronts. Okay, spherical wavefronts, but when passing through this lens, they will become planar wavefront. Okay, they will become planar wavefronts. Okay, so these are the planar wavefronts. Okay, because what does a convex lens do? So if we consider ray diagram, any ray that is coming from this position or the focus length, they will travel parallel to the principal axis. Okay, they will travel parallel to the principal axis. Okay, and in the wave picture, okay, and in the wave picture, the spherical wavefront will become a parallel wavefront. Okay, or the plane wavefront. Okay, and in case of plane waves, the amplitude, because the amplitude remain the same everywhere on this plane, the amplitude of particle or the amplitude of wave is same on this plane, so intensity remain the same on this plane. And if the spherical waves are very far away from the source, then the intensity remain constant over a long distance. Okay, so if we go here, then it will be constant on longer distance. So, okay, so it will be constant as we go farther and farther away from the point source. It will become more and more constant over a long distance. Okay, and it is sometimes more convenient to describe the wave propagation in terms of rays instead of wavefront. Okay, what is a ray? When a line that is drawn perpendicular to the wavefront. So this is the wavefront, then the line that is perpendicular to the wavefront is called a ray. Okay, so it shows the, so a ray shows the direction along which the wavefront moves, as in here. Okay, so the wavefront is moving there, and perpendicular to every wavefront is this ray of light. Okay, so this is about waves and wavefront and the ray. Okay, so what are the rays? These are actually perpendicular lines that we consider to the wavefronts. Okay, as we know, there are two types of optics: wave optics and ray optics. Okay, we see here that in case of this lens, that the ray optics and wave optics give us the same results. Okay, for these phenomena, okay, of reflection and refractions, but we cannot explain with ray optics the phenomena of interference, diffraction, etc. Okay, so now let us consider examples of waves, examples and types of waves. So waves can be classified according to the source that generates them. Okay, so source of generation, decides the wave type. Okay, the wave type. So we group them mainly as a mechanical wave, electromagnetic wave, matter wave, and gravitational wave. Okay, so let us first discuss what are mechanical waves. Let us now first discuss the what are mechanical waves. The mechanical or elastic waves are governed by Newton's laws. They are governed by Newton's laws and require medium. Okay, require a medium to travel. Okay, so they require a medium for their propagation. Examples are sound waves, seismic waves. What are seismic waves? The earthquake is a seismic phenomena. The wave they have is called a seismic wave. Okay, so earthquake is an example. Okay, seismic wave, water waves, they all needs a medium for their propagation and they follow Newton's laws. Okay, so that's why these type of waves are called mechanical waves. Okay, or also called the elastic waves. Okay, because elastic wave, they are called elastic waves because the medium follows rules of elasticity. They if the position of the particle is changed from its equilibrium position, it regain its position after some time. Okay, so that's why they are also called elastic waves. Okay, so sound waves, seismic waves, water waves are the examples. Okay, the next is electromagnetic waves. Electromagnetic waves. Okay, what are electromagnetic waves? Visible light. Okay, visible light. Radio waves. Radio waves. Microwaves. Okay, the microwave oven you use in your houses is contain microwaves. Okay, x-rays, gamma rays, these are all examples of electromagnetic waves. Okay, what they, as the name suggests, the electromagnetic wave consists of electric and magnetic fields. Okay, electric field and magnetic fields. Okay, and they do not require medium, so they do not require medium for their propagation. So electromagnetic waves can travel through vacuum also. Okay, but the seismic waves, water waves, sound waves, they cannot travel through the vacuum. Okay, if you scream in the if you scream into the space, then no one will hear you. Okay, because sound wave cannot travel into vacuum, they requires medium for their propagation. Okay, and all the electromagnetic waves travels with the same speed, which is the speed of light, represented by this letter c. Okay, this letter c, and the speed of light is approximately 10 into 3 into 10 raised to power 8 meters per second. Okay, the next is matter waves. Matter waves, so small particles or atomic particles, they exhibit wave properties under certain condition, and laws of quantum mechanics govern such matter waves. Okay, according to de Broglie, every particle which is having a momentum p have a wave associated with it. Okay, whose wavelength is given by this expression. Okay, this h is called Planck's constant. Planck's constant, it is a universal constant, and p here is a momentum of the particle. Okay, we know that momentum is mass times velocity. So particle uh, whose mass and velocity is given, it has associated with it a wave. Okay, and it is very strange thing, because the wave and particle properties are mutually exclusive to each other. Okay, for example, wave is spread throughout the region, but particle is very localized. It can be found only in one place, but the wave can be found in many places at same time. Okay, so if particle is represented by a wave, it means it can also be found at many times at the same time. Okay, so these type of waves are matter waves, the waves associated with small particles. Okay, well, they are also associated with large particles, but they are very small and not measurable for large particles, but for small particles they are measurable. Okay, next is the gravitational waves. So what is gravitational waves? So it was suggested that the cosmic bodies such as galaxies, stars, they produce gravitational waves and interact with each other through these waves. Okay, so the gravitational waves are believed to propagate with the velocity of light. Okay, and they were predicted in 1916 by Albert Einstein. Okay, so he predicted these on the basis of his general theory of relativity, GTR, general theory of relativity. So he considered them as a ripples in space time. Okay, and for the first time, scientists in the LIGO, it is a scientific collaboration with prominent role played by a researcher at MIT and Caltech. Okay, Massachusetts Institute of Technology and California Institute of Technology. They have directly observed the ripples of the gravitational waves. Okay, in an instrument which is present on Earth. Okay, the scientists have also decoded the gravitational wave signal and determined its source. So where these waves coming from. So according to their calculation, the gravitational wave is the product of collision between two massive black holes that were 1.3 billion light years away. Okay, light years away. So two massive black hole were colliding, and they generated these gravitational wave which were uh, detected by the observatory at LIGO, which is the researcher detected the signal with laser interferometer gravitational wave observatory. Okay, that's why it is called LIGO, which is a twin detectors. Okay, it's a twin, it's made of twin detectors, two detectors. Okay, which are carefully constructed to detect incredibly tiny vibrations from any passing gravitational waves. Okay, so once the researcher obtained a gravitational signal, they converted into a audio waves and listened to the sound of two black holes that were spiraling together into each other and then merging into a large single black hole. Okay, so this is all about examples and types of waves. So please like, subscribe, and please share the video. Thank you.